Finally, we ask that you just take a few minutes after the webinar to fill out a survey. It's short and should take only a couple minutes. Getting your thoughts will help us be more responsive to you. So with that, let's get started, Jim.
So, good morning or afternoon, depending upon where you are. I'm in Olympia, Washington. Am I being heard okay, Dave?
Yes.
Good. I'm going to start by telling you a little bit about myself. I've been an economist and working in the field since the late 1970s. I'm an economist, but I tend to stray into technical issues. I was a founding member of it was called the Regional Technical Forum here in the Northwest that advises the region on a whole host of energy efficiency and energy planning technical issues. I've worked with RAP since 1998 in about a dozen countries and about half of the states of the U.S. And I've been an author or a co-author on almost a dozen different RAP publications, several on rate design, some on energy efficiency evaluation, and the most recent one that we're talking about today, teaching the duck to fly. So what is this duck? If you haven't met the duck yet, you will soon, or you just have. The California ISO has prepared what's called the duck curve. I think it was actually first created by San Diego Gas and Electric. But what it shows, very simply, is that as more and more solar is added to the California power system, solar meets the mid part of the day load, but disappears at night. And that leads to a situation where in the late afternoon hours, the non-solar generation system needs to ramp up immensely, in this case from doubling its output in just 3 hours' time. And that is a very challenging ramping situation, we call it. There's also the risk in the middle part of the day of over-generation, that is, more generation being on the system than there is load, and something having to be curtailed. And we're experiencing this in California, in Texas, in Hawaii, and in Germany today, where there's, because of the baseload plants that can't be turned down, nuclear plants in particular, and coal plants that can't be taken below their minimums, we wind up with more generation than we can handle. The causes of this challenge are really pretty simple. We've had variable loads forever. The electric industry grew up with those. Wind is a variable supply. It's predictable sort of on an hour or 2 or 3 ahead basis. It's roughly predictable further ahead than that, but it clearly varies from day to day and from hour to hour. Solar is extremely predictable as to when it's going to be available, but it's predictably not available in the late afternoon when air conditioning loads and lighting loads tend to increase and the sun goes down. And but guess what? Ducks can fly. I mean, a duck in water has very much the shape of the California ISO graphic. The fat body floats, the tall neck breathes, and the duck just does fine in water. But a duck in flight has a whole different shape. It straightens out its body, stretches out its neck in order to have less wind resistance than it takes to wing. So our job today is to straighten this little ducky out. We're going to do that with 10 strategies. I've got 10 strategies. I have illustrative values for each. Not every strategy will be applicable to every utility. Some utilities have already done some of these. But the 10 are targeted energy efficiency, focus on the ramping hours. Orienting solar panels to the west to take advantage of the late afternoon sun. Using solar thermal energy for some of our solar energy so that it can be stored for a few hours. Managing electric water heat, making grid-connected, grid-integrated electric water heat. Requiring new air conditioners to include some storage capacity, chilled water or ice. Retiring older inflexible power plants, and that's happening anyway. Concentrating the utility demand charges into the ramping hours. If there are a few hours that are defining the utility's capacity requirements, let's concentrate the rate design in those hours. Deploying energy storage in targeted locations, so electricity storage, batteries or similar. Some aggressive demand response programs, many of which are underway in different parts of the U.S. And finally, interregional power exchanges. So what I'm going to do is I'm going to start off with an illustrative duck curve, a particular California utility that need not be named. It has a 4,000 megawatt peak demand, a 2,000 megawatt minimum demand, and that sharp afternoon ramp. The blue line here is the utility's total load without solar and wind, and the red line is the load that it will need to meet in 2020 after solar and wind are taken into account. And that red line has that very steep ramp up from 1,500 megawatts at 3 in the afternoon to 3,500 by 7 o'clock at night. This particular utility has for this day has a 63% load factor for the day and a maximum 1 hour ramp of 550 megawatts. A pretty challenging situation for a utility of this size. As compared to its total load, has a 73% load factor and a maximum 1 hour ramp of more like 400 megawatts, a little easier to manage. So that decline from 73% to 60% in load factor, the increase from 400 to 550 megawatts is the challenge that utilities are increasingly concerned about. So strategy 1, targeting energy efficiency. To focus efforts on measures with afternoon peak orientation. Now this measure that I've used illustratively has the utility conserving 5% of total usage by 2020. That's less than the rate of energy efficiency implementation in about 15 states in the country right now. So it's a very achievable level. But targeting measures have a 3-to-1 ratio between the on-peak savings and the off-peak savings. Kitchen lighting is a very good example of this. Kitchen lighting comes on at the time of the morning peak and at the time of the evening peak. Air conditioning is a huge contributor to the afternoon peak. So there's a number of specific measures that can be targeted for their afternoon peak orientation. And so with this 5% of total usage, the whole requirement shifts down, but shifts down more during the peak hours than during the off-peak hours. And here we see our duck shape. The faint line is where we started, and the dark lines are where we end after implementation of these energy efficiency strategies. And we've squozed the peak down and reshaped the duck just a little bit. The second strategy is orienting solar panels to the west. Most residential and most rooftop solar systems are on a fixed axis. That is, their racking is fixed. They only point one direction. And that output is a little more valuable if it's pointed to the west. Here graphically I show what the output is at 6 p.m. In blue, the panels are pointed south, and in green the panels are pointed to the west. You get about the same amount of total production, but you get a whole lot more production during the late afternoon hours. And here I assumed a 100 megawatt shift, taking it out of the earlier morning hours and moving them into the later afternoon hours. That's out of a total that this utility forecasts of 700 megawatts of rooftop solar. You'd need an incentive in the pricing and an incentive to the installers to take advantage of this, but it's a fairly modest strategy. And it shifts. Now you'll notice that each of these is shown compared to the cumulative effect of the strategies before. And we do this so that you can see that each one of these strategies makes a very small difference. And here you see that there's a little bit, the net load is increased a little bit in the morning because the solar isn't producing as much, and it's decreased a little bit in the afternoon when the solar is producing a little bit more. The third strategy is to use solar thermal in place of some of the solar PV. There are quite a few solar thermal systems around. They're a little more complicated, and they are more expensive than photovoltaics. But in the middle of this graphic, you see the key thing here, which is the thermal storage tanks. If the solar thermal system produces a hot fluid, it can be stored for a few hours and then used to produce electricity. Here I've substituted 100 megawatts of solar thermal for 100 megawatts of the utility scale photovoltaics that this utility is forecast. That's out of a total of 1,500 megawatts of utility scale solar. So I've only diverted a pretty small share of that to solar thermal. And once again, we've shifted the we've reduced the solar output in the middle of the day a little bit, and increased the solar output at the end of the day. So we've straightened out the neck of the duck here. We pressed up the belly and straightened out the neck a little bit. The fourth, and this is one of the most important and probably least well understood, is to control electric water heating. Grid control of electric water heating is an available technology. What you want to do is supercharge the tank during low-cost hours so it's full of hot water at a temperature hotter than we normally store water at. Install a blending valve, and blending valves have been around for a long time. They're actually mandatory in new shower valves that will blend the water back down to a temperature that the customer doesn't have any risk of being scalded. The graphic you see here is the control panel for the Steffes water heater control systems. They're installing high-efficiency super-insulated tanks that can take water up to 170 degrees. They get 25 kilowatt hours of storage per tank, and this shows that the tank is at 145 degrees, 146 degrees. It's hotter than you would normally keep a water tank, but it still has 8.8 kilowatt hours of storage capacity left in it. The illustrative utility has about 8 or 9% of the water heaters on its system are electric water heaters, according to the California Applied Survey. So I assumed it could gain control over a little more than half of those water heaters, which would allow it to shift 300 megawatt hours a day around in time. The nice thing about a supercharged tank is it holds a whole day's worth of hot water, so you can heat it up at any time of the day or night, and it will carry you for 24 hours. To get the water heating load off of the peak hours and put it into either the evening, the nighttime hours, or put it into the middle of the day when solar production is high. And here again, we shift the duct just a little bit. Each of these strategies is a small shift by itself, but you'll eventually see that this duct is changing its shape. Now, the water heat potential nationally is huge. Census data tells us that there's 45 million electric water heaters in the U.S. They use, when they're on, about 4 kilowatts each. So that's something like 200,000 megawatts. 200,000 megawatts of potential load that could be turned on during a period of overgeneration. Now, they're not all on at the time of the peak. About 20% of them are on in the afternoon, and they do tend to be a peak-oriented load. Think about yourself. You use hot water in the morning when you get up. You use hot water in the evening when you get home. So they do have a relatively, substantial contribution to the peak. About 40,000 megawatts could be shut off on peak if we had control of all the water heaters. And you can store, as I showed before, up to 25 kilowatt hours per tank. Now, a water tank that will store 25 kilowatt hours is under $1,000, and a battery bank that would store 25 kilowatt hours is on the order of $10,000. That's the battery pack that's in a Nissan Leaf. About a $10,000 battery pack. So in terms of capital investment, water heat is a very cheap place to store things. There's another thermal strategy here, which is to require new air conditioners to have 2 hours of storage. And there are a lot of air conditioners that have 12 hours of storage. But the strategy is to just have a utility standard that requires new air conditioning units over 5 tons, that is, larger than residential size, to include at least a couple hours of storage under grid control. And here I've moved 100 megawatt hours of air conditioning load out of the 6 to 8 p.m. period and into off-peak periods. The units you're looking at are the Ice Bear units from Ice Energy. They have several competitors that make packaged storage air conditioners. Proven technology, it works reliably. And it's important to understand how it works. On the left, you see the daily load shape for a typical office tower, a high-rise office building. Very low usage at night, but the lighting, fans, plug loads, pumps, and cooling comes on in the middle of the day. And on the right, you see what happens when you move that cooling requirement into low-cost hours. Now, this slide was put together in the context of a traditional time of use rate, but if the sun is providing a whole lot of power in the middle of the day, there's nothing that stops you from augmenting load in the middle of the day. And in Germany in particular, they're finding now with so much solar as they have on their system, that sometimes the middle of the day, noon, 1 o'clock, 2 o'clock, is the cheapest period of all. And some of the U.S. utilities are moving in that direction. I'm going to stop here for a second and ask Dave if we've got any questions that I need to address.
Jim, there was one in regard to strategy 2, orienting solar panels toward the west. The questioner, Peter Savio, wants to know what shift in degrees is required to do that.
The example I gave was from a study that looked at a full 90-degree shift from south to west, and I don't have the expertise to tell you what the optimal shift is, because as you shift off of south, you slightly reduce your total production during the day. And so there's some optimal point where you get the most value. And the only way to measure that really is to know the utilities cost curve during the day. And that actually will vary in different parts of the country.
Great, thank you, Jim. That's it for the questions. You can move along.
Okay. So strategy 5, this thermal storage could be a much larger resource. I've put in a pretty modest amount. It's really pretty dramatic. This is a slide from Texas. It shows what the difference is in load in residential, small commercial, and large commercial between a 64-degree day and a 109-degree day. The residential load is about 4 times. The commercial load almost double. Even the industrial load is higher. So getting control of air conditioning storage. Air conditioning is, on the order of 30% of peak demand on a lot of systems. There's 3 ways to get at air conditioning storage. One is a federal appliance standard that would require it nationally. Or California has adopted appliance standards on its own and possibly could adopt a regional appliance standard. The second is utility service standards. There are a lot of utilities that have existing service standards that say we will not serve certain types of loads unless they meet certain kinds of conditions. And it may vary from state to state whether utilities have the authority to adopt a standard like this and the regulator has the authority to approve it. But there certainly is the ability, I think in every state, for the utility to adopt a higher rate for service to uncontrolled air conditioners than it charges to air conditioners that have storage. A simple time of use rate will do that. A hookup rate, that is a capital contribution, is what will actually move builders and HVAC installers to change. And the third is a traditional utility retrofit incentive program and new building incentive program to entice the installation of storage air conditioners. So there are 3 ways to get this. I wanted to spend more time on storage, even though I've put a very modest amount. This 2-hour storage on 100 megawatts is a tiny little bite in our duck. I think that this storage air conditioners could be easily 10 times as big a contribution as I've shown, and storage water heaters could be 2 or 3 times what I've shown. And it's important to look at the cost differentials between thermal storage and other forms of electricity storage. This is a slide that was put together by Sandia National Labs that compares the costs of a whole bunch of battery options and pumped storage, hydro there in blue in the middle, and compressed air storage. The vertical axis here is the capital cost per unit of energy storage, for how much does it cost to build a battery to store a kilowatt hour in dollars. There's a logarithmic scale, 100, 1,000, $10,000. And the horizontal axis is the capital cost per unit of power, that is per kilowatt. This is what the electricity storage mechanisms have. I'm now going to show where water heater storage controls and retrofits fall in this scale, and where chilled water or ice thermal storage falls. It's 1/10 the cost of battery storage. So it's I think the most underutilized strategy we have available to us. Now, the sixth strategy is one that almost every utility in the country has either done, is doing, or is giving serious thought to retire older inflexible generating plants. Coal plants, nuclear plants, and gas steam plants are being retired because more than 75% of them in the country are 30 years old or older. They're just old. I mean, it's not, even apart from the pollution control regulations and water regulations that are forcing either high-cost retrofits or retirement, they're just old. And those of us on the phone who are old know that there does come a time to retire. But replacing them with much more flexible gas units that can ramp up quickly is a big opportunity. So we're retiring these, and we're building these. And the new GE Flex unit is designed from the beginning to be able to ramp up and down relatively quickly to follow varying loads and variable power supply. I've not produced a graphic of this. I've assumed that this strategy is already embedded in the utility forecasts. I'm not positive that it is. California is in the process of retiring all of the coal, but the retirement of the San Onofre nuclear plant was not scheduled and happened on, they went to do some repairs and decided it was too expensive to fix it. So there's no graphic there. Strategy 7 is concentrating demand charges. I mean, a typical utility right now has, for a medium-sized commercial customer, has a customer charge, I've put in $10 a month, a demand charge of $10 a kW that applies whenever the customer's peak occurs, whether it's 4 in the afternoon or 3 in the morning. And a dime a kilowatt hour. If we reshape these rate designs so that the demand charge, here I've put in $12 a kilowatt, but only applied in the 4 p.m. to 7 p.m. period. That is the steep neck of the duct, and the time of use rate. I think that we can get some pretty significant load shifts from customers. Now, this may be the rate design that stimulates the installation of storage water heat, storage air conditioners, and so there may be some overlap between, there's certainly some overlap between strategies here. But here I've assumed a modest reduction in peak demand and a modest increase in the off-peak demand in response to this strategy. We're, again, squeezing the neck of the duck and pushing up the belly of the duck here a little bit. The 8th strategy is to deploy electrical storage. To selectively charge electric vehicle batteries, RAP has a new paper out on this that will be published very, very soon on electric vehicles. That publication is actually aimed at the European market, but all the concepts in it are certainly applicable here. But also to possibly add some grid battery storage, but on strategic locations. That is, at areas where they will help avoid not only generation costs, but address areas where there's transmission and distribution bottlenecks and avoid T&D upgrade costs. In those targeted locations, we can actually find some cost-effective applications for batteries. I've assumed storage equal to 1% of the total load for the utility, energy use during the day, and 100 megawatts on this 4,000 megawatt utility. The ability to move 100 megawatt hours out of 1 hour and into another with battery storage. So it's a pretty small movement, but again, see here, it's a pretty small sliver on the duck. The ninth strategy is sort of traditional demand response, where we pay people to curtail during on an as-needed basis when the ramp is steep. And this is, I've assumed 3% curtailment of peak demand on high ramp days, on those days that are a challenge. Now, the New England ISL currently has 8% of its peak demand under contract for demand response. I've not assumed that, in part because the targeted demand charges and the storage air conditioning are already addressing a lot of the same loads. And unlike the other strategies, I'm not assuming that there's a shift of load from one period to another here. I think the other strategies have addressed an awful lot of valley filling and load shifting. So I'm assuming that this becomes 3% curtailment, economic curtailment, people who in response to a very high price or high offer for a couple of hours choose to not consume energy and they don't make it up some other time. Just let the building get a little bit warmer if it's an air conditioning measure that's being curtailed. I did that to keep the strategy a little bit conservative. And so here you see this occurring only during the top hours of the day at the very far right there at 7, 8, 9 o'clock at night, when the challenge is greatest for this utility. The 10th strategy is interregional power exchanges. There are a lot of interregional power exchanges between the Northwest and California. There's about 8,000 megawatts of transmission capacity. The Northwest is a morning and winter peaking region, and California is an afternoon and summer peaking system. So I have our sample utility taking advantage of the geographical diversity of loads, and this is important, the geographical diversity of the output from renewables, and exchanging about 600 megawatt hours a day into using the regional interties that California has to the Pacific Northwest, but also to Arizona, Nevada, New Mexico, and Utah. We're actually finding that the wind resource can have a very different shape in different parts of the West, and the integration for wind is important. And that's actually what's helping Germany with their very high solar saturation, is the fact that they're tied to a larger grid. This strategy obviously doesn't work for island systems like the Virgin Islands or Puerto Rico or Hawaii, where they're not interconnected to other regions. But here we've got it's a relatively modest shift relative to the amount of interconnection capacity that exists, but it's a pretty significant shift on this duck here. So this duck is just about ready to spread its wings and fly. So how did we do? Before the strategy and without solar and wind, we had a 73% load factor. And with the solar and wind, a 63% load factor. After the strategies, we now have an 83% load factor for the day. The hourly maximum ramp is now 340 megawatts versus 400 that's being met today, and 550 by 2020 with wind and solar and without these strategies. So we've got a system that's easier for the utility to manage than where we are today. I'm not going to go through these kind of one at a time, and we can look at them, how do we gradually have worked this duck. First with targeted energy efficiency, second by orienting solar panels, third by using solar thermal storage, fourth by managing electric water heater. I'm leaving the original load shape on in the faint lines here. fifth, by requiring new large air conditioners to include storage. The sixth is retiring older inflexible power plants, but I didn't include a change because I assume the utilities are doing this. The seventh is to concentrate the demand charges. The eighth is to deploy energy storage and electricity storage in some targeted locations, some demand response, and interregional power exchanges. So it's really quite a dramatic shift. Each individual strategy is pretty small. The utility won't need all 10 of them, but all or almost all of them are available to all utilities nationally. So this duck is about ready to take flight. And with that, I'm happy to take any questions that people have got. Dave, you're going to manage that.
I am. Thanks, Jim. That was great. So there are a bunch of questions, actually. Adam Garza says, I'm pretty surprised to see that time of use pricing was not listed as one of the 10 strategies. I thought you would have listed it number 1. The utilities send a strong price signal to retail customers on when to use and how much. Can they help mitigate the steepness in the duck chart?
Well, strategy 7 is a form of, I did introduce a time of use rate there, and I didn't identify a strategy. I talked about it as concentrating the demand charges. But if you look at this, I do have a time of use rate in there, and I guess I agree that it should be identified as a strategy. But that strategy requires that customers have new meters, whereas for the large commercial customers, we're talking about a very small number of meters, and they can be manually read. If you start putting in, if you have smart meters and a meter data management system that's working, you can implement that for all customers. But if not, targeting the large demand metered customers is a way of getting half to 2/3 of that benefit without the cost of deploying smart meters system-wide. But if there are smart meters, then the utility is able to do that for all customers.
Thank you. David Nemzoff has written, some of your strategies can be quickly implemented. Others require a longer turnover of capital stock. Have you tried to see if the timing of the strategies can keep pace over the years with the timing of the duck curviness?
Well, the duck is expected to get its top belly and its rigid neck by 2020, and I intentionally selected strategies that I think can be implemented in that period of time. I'm working right now with a utility on a deployment of a solar water heat storage program that is looking at replacing substantially all of the electric water heaters in the multifamily sector on their system over about a 2-year period. And multifamily is where a disproportionate share of the electric water heat is, because apartment buildings are often built with only cold water piping for the buildings. So that's a strategy that could be implemented in 2 years if somebody would get serious about it. Requiring new air conditioners to include storage is something that would phase in, but over 6 years, you would, if you caught the new and replacement air conditioner market, you would have about 1/3 of the air conditioning load under control by 2020. So I think, by and large, these are strategies that can be implemented at the level I've suggested over a 6-year period.
Mina Burko wants to know if there are any states that employ the AC strategy already, and can you name a few examples?
There are a lot of, I'm not aware of any state that mandates storage air conditioning, but there are states where storage air conditioning in large commercial buildings is standard practice in new construction. California is one, and it's becoming more common in Texas. On the other hand, there's just a phenomenal retrofit opportunity. I was just in Hawaii, where electricity is 40 cents a kilowatt hour, and talking to a couple of HVAC workers there, and on the whole island, there's only one system that's got storage on it, and there's just they're spilling wind at night, and the economics of substituting surplus wind for petroleum-generated electricity are as good as they could be anywhere. So it's a huge retrofit opportunity, but it's not uncommon in large office buildings and hospitals and that scale of construction.
I'll try to get this question correct. Don Ferber writes, doesn't the increase in residential load under heat mean more needs to be done for residential than commercial to manage peak loads, or is there a time variance when that load hits?
Well, the peak, really happened, the afternoon peak is a coming together of residential loads rising and commercial loads staying high. At 5 o'clock, commercial loads are all on, and the residential load is coming back from the midday slump. Kids come home from school and people come home from work. The retail load is on until 9 o'clock or 10 o'clock at night, and the residential load peaks during that period. The residential peak is, typically 6 to 7 p.m. The commercial peak is 4 to 6 p.m. They collide in the 5 to 6 p.m. period, and that combination does create the peak for most systems, for summer peaking systems. And so I did include the targeted energy efficiency and water heat storage as residential strategies. I don't disagree that some better targeting of residential air conditioning. I did not include residential air conditioning cycling because many utilities in afternoon summer peaking regions already have very strong programs. Southern California Edison has thousands of megawatts, has over 1,000 megawatts of residential air conditioning under demand response program that's been in place for 30 years. So that one resource has certainly been proven, and in areas where it has not been deployed, it belongs in this strategy list.
Thanks, Jim. Back to the reorientation of PV arrays. Tilting solar, how can installers be incented? And can you use traditional TOD factors, and if so, how?
I'm not a solar installer. I don't have expertise to answer that. But I can the technical side of it. The incentive side can a time of use rate does provide that incentive, or where there are utility cash incentives for installing solar, which there are on many systems. They can be, $200 a watt if they're pointing south, and $3 a watt if they're pointing west, or something to that effect, and the incentive will show up in the rebate amount.
Okay. Kevin Porter wants to know if many of these issues being described in this presentation would go away if the utility in question were to join the Cal ISO.
It's a member of the Cal ISO. And I don't think, none of the strategies go away, nor does, and the Cal ISO has a need for all of its members to pursue strategies like this to address what it sees as the emerging duck problem.
Okay. Patrick Keegan asks you to elaborate on targeted energy efficiency. The question is, does energy efficiency that doesn't meet the 3-to-1 ratio make the problem worse?
Well, energy efficiency that occurs during off-peak hours may make the problem worse. Energy efficiency that doesn't curtail the afternoon peak may make the problem worse. I mean, in that sense, improving the efficiency of high school stadium lighting systems that are on at night only, or street lighting. So street lighting systems is a better example. They're dusk-to-dawn systems. In the summertime, dusk isn't until after the neck of the duck, and probably by removing some off-peak load may make the ratio of maximum peak load to minimum off-peak load worse. Most energy efficiency, or on average, energy efficiency has the shape of the system load. And so it's not very difficult to identify which are the off-peak resources, and if you simply reduce efforts in those areas and concentrate on the other areas, you're going to get peak concentration. I mean, the average conservation program has a 2-to-1 peak to average ratio. I propose moving it to a 3-to-1 ratio. But it would require higher valuation for some measures and programs and lower valuation for others.
David Nemtsov offers the following observation, Jim. Thermal storage is in fact often cheaper than other storage and more energy efficient, but it doesn't send electrons back into the grid, and that leads to a big pair of barriers. It's harder to quantitatively value using conventional utility/commission valuation methods, and there's a cultural barrier within utilities and the industry. It's a modern variant of negawatts versus megawatts.
Well, I'll flip the question between water and air conditioning heating, because the thermodynamics are different. With water heating, the electric utility actually may be better off, because I'm going to back up to the slide here that shows the control panel for water heat. When you raise the temperature of the water in the tank, you actually have slightly higher standby losses in the tank. The water in the tank, in this case 146 degrees, it's going to be losing more heat into the room than if it were 120, which is what you're supposed to set your tank at under the 93 Plumbing Code amendments. And so the utility is actually selling a few more kilowatt hours to the customer. But it's selling those kilowatt hours at off-peak periods and not selling kilowatt hours at on-peak periods. So the utility's line losses are lower. The utility is in the wonderful position of selling more kilowatt hours at the meter, but producing fewer at the power plant. So it's a huge profit maker for a utility that does not have a time of use rate. Now, in order to entice customers to participate, you need to give them a financial incentive, and you certainly need to make them whole for their line losses. But the utility still gets you need to make the customer whole for the standby losses. But the utility still gets the benefit of significantly reduced line losses, because the on-peak losses can be 2 or 3 times the marginal off-peak line losses. And REP has a paper on that we published a couple of years ago. In air conditioning, it is different, because the chiller has higher efficiency at night and uses fewer kilowatt hours to produce the same amount of cold than it would during the day. And so there is a net energy conservation effect. But I don't think we run into the problem that we often do in, for example, in fuel switching programs, where the utility can completely get rid of this water heating load by incenting customers to shift to gas water heat. my assumption is that the controlled electric water heating will only be applied in areas where electric water heating is going to continue. Rural areas where gas is not available, and multifamily. I don't see these as actually nearly as challenging from a utility perspective as the concentrated energy efficiency is, or for that matter, as rooftop solar is a challenge to utilities financially.
Jim Edelson asks, are the building strategies, in other words, the efficiency in the AC storage, demand shift quantities based on new construction rates, or are they applied to existing buildings?
I assume in choosing the amount available, I assumed that the utility was able, in essence, to get all of the replacement market and none of the retrofit market in water and air conditioning. In targeted energy efficiency, I just said it was 5% of total load being conserved, and that compares to up to 2% a year in the best performing states, Massachusetts, Vermont, 1.5% in Minnesota, so on an annual basis. So those would be 9 to 12% over 6 years, and I've assumed 5%.
Typical demand response results in a bump after being dispatched, often as large as the dispatch itself, says Jason Ledbetter. Do you believe this can be avoided by some means? It appears as though this was assumed in your model.
The modest assumptions that I made are indeed assumed, and I guess I would look to New England as the region with the best developed market for demand response for experience and field results.
Okay, Jim, we're winding down here. You have time for a couple of, this is the lightning round, time for a couple quick responses. Henry Yoshimura wants to know if you have cost estimates for each strategy.
No.
Okay.
The water heating is cheap.
Okay. Pierre Bull wants to know what grid connection standard are you seeing emerge as the most common? For example, open ADR with grid-connected appliances and equipment?
I don't know.
Okay. What is the most appropriate mechanism or mechanisms by which to implement these strategies? An IRP approach where the utility implements the strategies with rate recovery, appropriate rate designs that incent customers to implement the strategies, targeted incentives, subsidies to get customers, or perhaps ESCOs to implement some of the strategies, a combination of the approaches?
Definitely a combination of the approaches. But and I would add third-party administrators like Efficiency Vermont to that list.
Okay. Well, Jim, I think it's about 5 minutes of, and I think this is a chance for you to just reiterate some of your observations. We didn't get to everybody's questions, but I think we covered nearly all of them. So I'm going to hand it off to you, Jim.
Well, first of all, I'll have Dave get me all the questions we didn't answer, and we'll answer those in writing to the best of our ability. What I've tried to do is to just show that while each strategy by itself is pretty small, that when you take a coordinated approach using a multitude of strategies, that reshaping both the electric load and the electric supply is something that we can do. Some of these may seem like they are heavy-handed, but the alternative is also heavy-handed. The alternative is either very sharp increases in electricity prices, sharp restrictions on the installation of customer-owned generation, or deteriorating electric system reliability. and I don't think that any of those alternatives are acceptable. Each of the strategies that I've identified has been deployed and proven to work. There are good pilots and in many cases good widespread programs for each of these, good models for what we can do, what we should do, and I think what we must do. They're not the only strategies. There are some that I didn't include, and certainly time of use rates in sectors other than the demand-metered commercial sector is an area that is valuable for systems that have the metering and meter data management to handle it. The bottom line is this industry has evolved over 125 years adapting to changing generation technologies and changing consumption patterns. That's all we have to do to adapt to solar and wind, but we have to do it much faster. Fortunately, we have much better tools available than our grandparents and great-grandparents had to do this, and if we fail, it's our fault.
Thank you, Jim. Thank you, everybody. We've come to the end of our webinar. We encourage you to fill out the survey. Please take a couple minutes and do that. And remember that Teaching the Duck to Fly is available on the RAP website. We hope you've enjoyed this. Have a great rest of the day. Bye now.